Bismillahirrahmanirrahim. Assalamu alaikum students. How are you? I hope you will be fine. And I hope you have studied all the previous lectures related to the Poisson equations and Laplace equations in the electrostatics. Because we are now dealing with the electrostatics, not with the electrodynamics. There is a big difference between electrostatics and electrodynamics. In electrostatics, we deal with the charge in the rest in the statics condition. And in electrodynamics, we deal with the charge moving, not in the rest, but in the dynamics. That's why it is termed as electrodynamics. Now, today, we will discuss electrostatics topic, the Laplace equations. We have studied the Laplace equations. We have derived it, but now we are going to solve it in two variables, in two dimensions. In the spherical polar coordinate system, we have studied three types of the coordinate system. One of them was the rectangular coordinate system, and the second one was spherical polar coordinate system, and the third one was cylindrical polar coordinate system. And today we will discuss the solution of this Laplace equation in spherical polar coordinates in two dimensions, means using its two variables, its two coordinates of spherical polar coordinate system. So we started. We will solve Laplace equation where phi is a function of more than one variable. We know that phi is what? Phi is the potential, that is the variable of the Laplace equation. And if it is a function of more than one variable, means if you are talking in the rectangular coordinate system, you say that it's a function of x and y, not only x. In the similar fashion, if you are dealing in the spherical polar coordinate system, you can say that the Laplace equation, the variable of the Laplace equation, phi is a function of r and theta, not only r. R is the first variable, first coordinate, theta is the second coordinate, and phi is the third coordinate. Because we know that r, theta and phi are the three coordinates of this spherical polar coordinate system. So over here we will discuss only r and theta. For the spherical case, phi is phi of r or theta, where r is the radial vector and p is the polar angle. So we have written phi as function of r and theta. In the brackets, there are two coordinates, r and theta. Therefore, the Laplace equation that we have studied, d square phi over d r square is equal to 0, was that we have written in these two coordinates the whole Laplace equation, like 1 over r square partial by partial r square partial phi by partial r plus 1 over r square sine of theta partial by partial theta into sine of theta partial phi by partial theta is equal to 0. Means this is the first part of the equation consisting on the first coordinate r, and this is the second part of the equation consisting on the second coordinate theta. And this partial differential equation will be solved by a technique known as separation of variable method. I hope you have studied the separation of variable method in mathematical physics, that when you have two variables in an equation, then you use the separation of variable method and you separate the equation into two variables on both sides of the equation and equal to one constant. This is the separation of variable method. And over here, the solution of the form phi of r over theta is equal to zr p theta. Look, this is variable phi, function of r and theta. We have written it is equal to two parts, two components, z and p. Z is function of r, p is function of theta. Phi r theta is equal to z r p theta. This first component is related to this coordinate. The second component corresponds to the second coordinate. So this is a separation of variable method. So we will substitute this equation in equation number 1. Instead of phi, we will write equal to z multiplied by p. Phi is equal to z multiplied by p. First component z is a function of radial component r, and the second component p is a function of theta, polar angle theta. Okay, we will put it in the equation number 1 over here, phi, and over here. Then after substituting this equation in this equation number 1, the simple modification in this 1 will occur, and the equation will become 1 over r square p of theta d by dr r square dz by dr plus dr over r square sine of theta into d by d theta sine of theta d by d theta is equal to 0. Mean over here you wrote zp and p will be outside this partial derivative. Why? Because this derivative is with respect to r, and the term having theta will be considered as constant. Therefore, we have taken it outside the derivative. P of theta is outside d by dr derivative. And similarly, in the second term, you wrote over here instead of phi z and p, z multiplied by p, but you took z outside this derivative because the derivative is with respect to polar angle theta, and r is constant for this term. Therefore, z of r will be treated as a constant in this term, and you have taken it out of the derivative, out of the context. Now this equation will be divided by phi r theta and multiplied with r square, because multiplication with the r square will eliminate this r square and r square, and we will divide with phi of r by theta. By dividing this, we will draw this p of theta from this component and z of r from this second part of the equation. This is the reason that why we have divided with phi function of r and theta. So after this simple mathematics, we will get 1 over z d by dr in r square dz by dr is equal to minus 1 over p sine of theta d by d theta into sine of theta d by d theta. This will be our equation number 3. So we have done what? We have separated into two forms. One form is with respect to radius, and the second is with respect to the polar angle theta, and both are equal to, because the whole is equal to 0, so you can take it out on the right hand side of the equation with the negative sign. No problem. This left side of the equation is a function of r only, and right side is a function of theta. Yes, you can see no theta is involved in this term, no r is involved in this term, in this part. Why? Because we have divided with phi r of theta and multiplied by r square. This is the reason behind this story. The only way in which a function of r can equal a function of theta for all values of r and theta is for both functions to be at constant. You want to make this equal to this, and this is only possible if you make both of these terms equal to a single term, that is constant. Hence select each side of equation number 3, left side and right side equal to k. We will put left hand side is equal to k and right hand side is equal to k as well. K is constant and is called the separation constant. Now we will consider the theta equation, this part, right hand side of the equation number 3, and this is known as Legendre equation. We will consider only this part, right hand side part, the equation involving only theta, and this is called Legendre equation. So what we get? We get 1 over sine of theta d by d theta into sine of theta dp by theta plus kp is equal to 0. Why this term? Because we wrote we will assign a constant equal to both sides. That constant is k. So we placed this equation equal to k, this equation equal to k, and p was multiplied with that k. That is why there is no p over here, and this kp will be brought to the left side again, and after that we get this equation. The only physical acceptable solution that are defined over the full range of theta from 0 to pi correspond to k is equal to n into n plus 1. Now we will have to solve this equation, this Legendre equation, and the solution is possible when theta's value is from 0 to pi, because it's polar angle and its value should be equal to 0 to pi, and this is only possible when you take this k is equal to n into n plus 1. N is a positive integer. This constant k is equal to n into n plus 1, and n is positive integer over here. The solution for a particular n will be denoted by p and theta. When you solve this equation, and that solution will be written as p and theta, and this solution p and theta, the acceptable solution p and theta, are polynomials in cos of theta and usually referred to as Legendre polynomials. So when you will solve this equation, you will get the solution. What will be that solution? Pn of theta, and you will term this solution as Legendre polynomials. And then the first 4 Legendre functions of after solving this equation will be for different values of n, because we have taken k is equal to n into n plus 1, n will be 0, 1, 2, 3, and putting these values, after solving this, putting the values of n in Pn of theta, you will get for 0, Pn of theta will be equal to 1, for n is equal to 1, Pn of theta will be equal to cos of theta, and when for n is equal to 2, Pn of theta will be equal to 1 over 2, 3 cos square theta minus 1, and for n is equal to 3, Pn of theta will be equal to 1 by 2 into 5 cos cube theta minus 3 cos of theta. These are the Legendre polynomials obtained from the solution of this equation, that was Pn of theta. Now we come to the second part of the equation, that was radial equation. The equation, the part that only consists on the radial factor, radius of the sphere R. That was this one, d by dr into r square dz by dr is equal to, because we said that we will also keep this equation, this part equal to k, and k is equal to n into n plus 1, and this z will be multiplied by on the right hand side with n into n plus 1. That's why we will get this equation number 5. Inspecting this equation number 5 shows that the independent solutions are from this equation. If you solve this differential equation, you will get the value of z. Likewise, you got the values of Pn of theta, you will get the values of z. Zn is equal to Rn, Zn is equal to Rn. There will be two types of values here that you will get from this equation. In general, solution of the Laplace equation are obtained as the product phi of n r of theta equal to Zn r Pn of theta. This was a very specific case when you wrote phi of r theta is equal to Z r P theta. In general, you write n over here. Phi n r of theta is equal to Zn r Pn of theta. And therefore, solution of the Laplace equation in spherical coordinates have been obtained that are known as zonal harmonics and are given as phi of n is equal to Rn Pn theta, or phi of n is equal to R minus n plus 1 Pn of theta. So these are the zonal harmonics obtained for the Laplace equation in spherical polar coordinates. Because we wrote in the caption, in the title of the article, that zonal harmonics. So this was our today's topic that we have discussed. We have written the Laplace equation in two coordinate system. One was r and second was theta. And then we separated this equation using the separation of variable method, and we used a separation constant k and assigned it a value of n into n plus 1. Then we solved both parts, radial part and polar angle part, and we got some values that were called the Legendre polynomials, and in general the values of this solution of this equation resulted in the zonal harmonics. Up to now, if you have any question, you can put over here. You can ask me. Okay, thank you very much. If you have further any question, you can ask me via my WhatsApp number, or you can comment on my video. Thank you very much. Thanks for watching.